So design analysis of column steel base plate. Okay, so the objective of this discussion is to come up with the design wherein we're going to solve for the required P by N and its corresponding thickness T. So for these figures, so this is an elevation view while this is a plan view, okay, of the assembly on the steel base plate. So I have here the pedestal. Usually this is made from concrete. Okay. Then on top of this, we have a steel base plate here. Then wherein the column is resting. Now the question is, how do we connect the column, the white flange column, with the steel base plate? How do we connect them? Since they are made of steel, both of them are made from steel. So we can connect them through welds. No? So what about for the steel base plate with the pedestal? How do we connect them?
Bolts.
So we can have it anchored. So using anchor bolts. Okay. Now, why do we provide steel base plate in between them? So one reason is to widen up the contact area between the column with the pedestal. Kasi without the base plate, the contact between the wide flange column and the pedestal would be the area on the pedestal. And that would be critical against bearing. And that may lead to punching shear failure as well. So to widen up the contact area between the column and the pedestal, we provide a certain area for the steel base plate. So instead of the column in contact with the pedestal, there will be a contact between the base plate with the pedestal now. Okay? So how do we design column base plate? So in designing, so we need to identify, we need to foresee the possible failures. What are the possible failures do you think would be in this assembly of a base plate? Okay, so what are the two major failures that may happen in this assembly? Okay, so bearing, so that's correct. Okay, the first critical failure is bearing stress. Where bearing stress will happen? Particularly in what material? So the bearing stress may develop between the pedestal and the steel base plate, diba? So between the pedestal and the base plate, where do you think would be this stress failure will happen? Huh? Saan? So most probably this will happen on the bearing stress failure on the side of the pedestal. Okay? So let us consider bearing stress failure on the pedestal. Okay, so as we all know, bearing stress is force all over area. So we can solve for the area required for the base plate by having the column load P divided by with the capital FP. Okay? Again, P is the column load, while FP is the allowable bearing stress on the pedestal. And what would be the capital FP? So this actually depends on the type of pedestal being used. So as per NSCP code provisions, we have here different pedestals used for base plate. So if we will be using limestones and sandstones as pedestal, the allowable bearing stress would be 2.75 as per NSCP. If we will be using bricks in cement mortar, usually these are the adobe type of material, the allowable bearing stress for that case would be quite smaller, and that is 1.72 megapascals. The usual material used for pedestal are concrete. So we have two cases here for concrete support. One is whenever we have a full area of the concrete support, and the other one is whenever the base plate is resting on less than the full area of the concrete support. So the allowable bearing stresses would be 0.35 of FC prime for full area. Then for less than full area, 0.35 of FC prime but we need to multiply it with this factor, which is square root of A2 over A1. Upon computing for this capital FP, we have to check it with the limit set by the code that it should be less than or equal to 0.7 of FC prime. Okay, so take note that FC prime, as we all know, that is the 28-day compressive strength of concrete. Okay? This may be possible if this would be the pedestal and the area of the base plate coincides with the area of the pedestal. So this means full area. So if the pedestal is like this, and if your base plate is less than the full area, so this would be less than full area. Okay? So for this case, our allowable bearing stress is to be taken as 0.35 of FC prime, while in this case, 0.35 of FC prime, but we need to multiply it with this factor of A2 divided by A1. Now, what are these A1 and A2? From this definition, A1 is defined as the area of the steel concentrically bearing on concrete support. Meaning to say, that would be the area in contact between the two materials. In short, this corresponds to the area of the base plate in contact with the pedestal, A1. How about A2? A2 is the maximum area on the portion of the supporting surface, which is the pedestal, that is geometrically similar to and concentric with the loaded area. The loaded area is referred to as the area of the base plate. Example, let's say I have a square pedestal, say 500 by 500. Okay. Then let's say I have a square base plate also, say 250 by 250. Question: what is A1? What's A1? The area in contact between them. So that's the area of the base plate. That is 250 by 250, right? How about A2? Okay, A2 is the largest area, the maximum area, okay, the maximum area on the pedestal, which is similar to the area of the base plate. So if our base plate is a square, what would be the maximum square that we could have inside the pedestal? It's also 500 by 500. Yes, so that's A2. Now, what about if you have this case? Let's say I have a rectangular pedestal, say 300 by, say, 600. Then, I have a square base plate, say 250 by 250. So, what is my A1? 250 by 250. What is my A2? Okay, so that would be the maximum square, similar to the base plate that we could have inside the pedestal, and that would be 300 by 300. Okay? Now, what about if I have this case? Let's say I have a rectangular section, say 450 by 700. Then my base plate is a rectangle also. Let's say 300 by, say, 550. So what is my A1? 300 by 550. Okay. What is my A2? What is our A2? Again, as per definition, A2 is the largest rectangle similar to this that we could have inside the pedestal. So if this is a rectangle, let's say this would be A2. I'm assuming that the red rectangle would be A2. So if that would be my A2, this dimension would be 450. What about this dimension of the red rectangle? Let that be a Z. Let that be a Z. So how can we solve for that Z? The blue rectangle, which is the area of the base plate, should be geometrically similar to the area on the red rectangle. So basically, A2 would be 450 times Z. But what is Z? By ratio and proportion, they have to be geometrically similar. So by ratio and proportion, we have Z is to 450. Z is to 450 as to 550 as to 300. Okay? So can you give me the value for Z? What is Z?
825.
Huh?
825.
What's the answer from your calculator? 825. Okay? So what does it mean?
So, kulang siya.
825, this is the Z, compared to the 700, that is greater than 700. So it cannot be that value. So we have to revise our figure. So this is not okay. So we have to revise it. Say 450, then this is 700. This is the base plate, 300 by 550. So instead of having this red rectangle like this, it should be like this. So for that case, this would be 700 and this would be our Z. Follow? Therefore, our A2 this time would be 700 times Z. But what is Z? Z is to 700 as to 300 is to 550. What is Z therefore? So, of course, our Z value should be less than 450 to be acceptable. And that is